There are mysteries in the depths of the world that both scientists and dreamers are interested in. Today we're taking another trip to space, from Earth's mysterious Great Unconformity to the mysterious Great Void. Our research has always brought us further, and we learn about the mind-boggling idea that the universe is expanding. And this time, even greater news: stars are disappearing. But first, what is the Great Unconformity? The Great Unconformity is one of the most puzzling geological secrets. It comprises over 1 billion years of missing rock layers not laid down and stacked like the rest of the geological record. It's like those years didn't happen. In 1869, scientist John Wesley Powell was traveling down the Colorado River when he saw this strange gap for the first time. We'll be able to date these sections in the future. Some places of rocks formed between 1.4 and 1.8 billion years ago, and rocks formed only 520 million years ago. You can see clearly that rocks have been pushed together at the bottom. Their layers go up and down. Then there's a break, and above that are these beautiful horizontal layers that make the Grand Canyon's buttes and peaks. So what happened to the other rocks? In a new study, scientists suggest that the Grand Canyon's history is more complicated than previously thought, and that different parts of the site may have moved in different ways over the millennia, causing some rock and sediment to be washed away to the ocean. Scientists have come up with new methods, and the main part of these new methods is thermochronology, which uses several chemical analysis techniques to figure out how much heat was stored in rocks when they were formed. The amount of pressure that geological forms are under is the same as the amount of heat they give off. The gaps in the geological record are likely caused by several small but important faulting events based on the data collected by the researchers. These would have happened around the same time the supercontinent Rodinia broke up violently, between 633 and 750 million years ago. This was a time when the Earth's tectonic plates were moving around a lot, which may have made it so that the rock layers didn't settle in a more even way. The results, however, aren't enough to solve the mystery of the Great Unconformity for good, but they are a good step in the right direction. The researchers also think the same methods can be used in other places in the US where similar geological twists have been seen. What is certain is that the Grand Canyon continues to amaze people, both because of its natural beauty and because of the way it shows the Earth's geological past over billions of years. But gaps aren't only on Earth. It happens in space too, from the Great Void, well known as the Boots Void, to the supervoids. But these mysteries are for another day. It's been over a century since physicists proposed that our universe is expanding and that the more away a galaxy appears to recede from us, the faster it appears to expand. This is not because galaxies are physically moving away from us, but because the universe is filled with gravitationally bound objects, and the fabric of space in which those items live is expanding. However, this depiction, which was prevalent from the 1920s onward, has recently been altered. It's just been 20 years since we first noticed that this expansion was accelerating, and that as time passed, individual galaxies appeared to recede away from us quicker and faster. Even if we travel at the speed of light, they'll become unreachable in time. Because the speed of light is limited, when you look at a star whose light gets to us after traveling for 100 years, you're viewing a star that's 100 light years away. And when you look out at a galaxy, its light arrives after traveling for more than 100 million years towards you. You're not staring at a galaxy that's 100 million light years away. Instead, you're looking at a galaxy that's a lot farther away. The exact reason for this is that the universe is expanding on the biggest sizes, items that aren't gravitationally tied together into galaxies, groupings, or clusters. The longer it takes a light particle to travel from a rather distant galaxy to us, the more important the function of the universe's expansion becomes. Meaning that the most distant galaxies are even further away than the period their light has been traveling. This manifests as a cosmic redshift. We fully expect the light to arrive at its destination with a specific wavelength because it's emitted with a specific energy and thus a specific wavelength. That wavelength would be the same if the fabric of the universe was neither expanding nor contracting but rather constant. However, as the universe expands, the fabric of space stretches and the wavelength of light lengthens. The large redshifts reported for the most distant galaxies have unequivocally confirmed this image. But we can do far more than simply determine that the universe has and continues to expand. We can use all of the knowledge we've gathered to deduce how the universe has expanded over time, which informs us what the universe is made of. The expanding universe expands the wavelength of light once it leaves a distant cosmic source. This causes a redshift, in which the light of more distant objects redshifts for longer periods, when other components of the universe, such as dark energy, matter, or radiation, are more important. We can rebuild the complete expansion history of the universe by measuring sources at various distances, discovering the redshift, and then measuring their intrinsic versus apparent size or intrinsic versus apparent brightness. Furthermore, because the way the universe expands is dictated by the different forms of matter and energy present, we may understand what our universe is made of. Once we know the exact components of the universe with precision, we can simply apply this to the rules of gravity and predict the fate of our universe. When this was applied to the discovery of a dark energy-dominated universe, we observed something shocking. To begin with, it meant that any galaxies that were not already gravitationally tied to us would gradually vanish from view. They would accelerate away from us, continuously increasing as the universe continued to expand, unabated by gravity or any other force. The galaxy would get more distant with time, implying an increasing quantity of space between that galaxy and us. Because of the expansion of space, the galaxy appears to be moving away at increasing rates. However, this leads to an unavoidable and frightening conclusion, and means that at a certain critical distance from us, a photon, either leaving our galaxy for a distant one or entering ours from a distant galaxy, can never reach us because of the expansion of the fabric of space. The universe's expansion rate is so vast that distant galaxies become inaccessible to us, even if we move at the speed of light. At the moment, that distance is only around 18 billion light-years away, as the density of matter and radiation continues to fall, as does the total expansion rate. Given that our observable universe has a radius of 46 billion light-years and that all regions of space contain the same number of galaxies on average, and on the largest scales, this means that only about 6% of the total number of galaxies in the universe are currently reachable by us. It also means that, on average, around 20 and 60,000 stars transition from being reachable to unreachable every second. The light they emitted a second ago will eventually reach us, but the light they emit right now will never, thus disappearing. It's a scary, sobering concept, but there's another way to look at this. This is the universe reminding us how valuable every second is. It's the universe reminding us that if we ever want to go beyond our own local group, the gravitationally bound set of objects comprised of Andromeda, the Milky Way, and around 60 small satellite galaxies, every instant we wait is another opportunity lost. As time passes, humanity will remain trapped in our local group unless we achieve the capability of intergalactic travel and venture out to other galaxy groupings and clusters. Our ability to send and receive signals to what is beyond in the vast cosmic ocean will gradually fade from view. The universe's fast expansion is unstoppable, and our gravity is insufficient to counteract it. So one thing remains clear: the universe is vanishing, and we have no control over it.